Hi, and welcome back to Allen High School's discussion of electrochemistry at the AP/IB/HL level. Now, let's do some examples of spontaneity and the EMF and how to balance simple half reactions. Now, in this case, I have aluminum ion and, I think I wanted this one. All right, so what we want in this case is we want to set these up to be spontaneous. You may have to do that. You may be given two half reactions and you need to figure out what needs to be oxidized and what needs to be reduced in order to have a spontaneous reaction. So we have two half cells, and what we want to do first is look at their E0 values. So for silver being reduced, the standard reduction potential is positive 0.80 volts. And for nickel, it's minus 0.25 volts. Now, since the problem tells us we want a spontaneous system, that means that we want our most positive to be reduced and our most negative to be oxidized. You need to know it that way. You really need to understand those signs. So we're going to let silver be our reduction half reaction. So we have silver plus 1 electron gives us solid silver. And I'm going to keep the E0 exactly as is. And for our nickel, I'm going to reverse it because we need that to be our oxidation half reaction. And since these are metals, we will, that should be solid there, sorry. Since these are metals, we'll be able to use them as electrodes as well. Now, since I reversed this, notice that I have to change the sign of the potential there. Now, if I want a balanced overall reaction, I need to exchange the same number of electrons. This is pretty straightforward. I'm going to multiply this by 2. But notice I do not multiply E0 by 2. And if I did that, my balanced overall reaction would be 2 silver ions. My electrons will cancel, plus a nickel gives you 2 silver solids plus 2 nickel ions. Now, I just add these up to get my EMF, and I have a positive 1.05 volts, which is confirmation that we set it up correctly. If we were looking for spontaneous and you had a negative there, you know to go back and erase what you did because you blew it. Okay, now let's go ahead and calculate delta G0. So delta G0 is minus NFE naught. And we exchange 2 electrons, so that's minus 2 times Faraday's constant, 96,500, times our E0, 1.05, and I get negative 203,000 joules, or a negative 203 kilojoules. Again, a negative delta G is spontaneous, so further confirmation that we set this up correctly. Now, we don't want to have to draw cells all the time, so scientists came up with a shorthand notation. Now, when you do cells, there's not always a convention that left is the oxidation and right is the reduction. That's not always the convention, so it's not always true with cell pictures. Often it is, but I wouldn't count on it. And in fact, they may actually, reverse that order to see if you understand. But when we do cell notation, the left-hand side is always representing the anode or oxidation side, and the right-hand side is always going to be our reduction or our cathode. So let's take a look at the notation. Since we have nickel being oxidized, what we would do is we would write our solid nickel, sometimes with states, sometimes they're sloppy about that. And then what we're going to do is draw a line. That line indicates a phase boundary, because what we're going to write next is the nickel ion, nickel 2+. So a line indicates a phase boundary. Now, what the convention here gets a little dicey. Sometimes you'll simply see an aqueous. Sometimes in parentheses you'll see 1 molar, or if it's a non-standard cell, you may see something like 0.1 molar, some non-standard in the parentheses. Now, honestly, there are times you'll see this, aqueous, comma, 0.1 molar. So I'll look it up whenever you have this on your WebAssign and try to give you some guidance, since there's not always a clear convention on that. Now what we're going to do on this is put 2 lines. The 2 lines represent our salt bridge, without which the cell would not operate. Now I'm going to do my reduction half reaction. In reduction, we took silver ion. Notice we don't have the balancing coefficients in here. Aqueous, or possibly 1 molar, comma. No, I don't want a comma. Sorry. Silver ion. We'll see that comma in just a minute. And then I have a phase boundary with my silver electrode. So I'd have Ag solid. So that's our convention for writing cell notation. Let's do one more, and then we'll do a non-spontaneous situation. Again, we're setting this up to be spontaneous. So if we looked up our E0 reductions, we'd have minus 1.66 volts for the aluminum half reaction. We'd have plus 0.53 volts. Hopefully that's logical to you, that iodine, a non-metal, would prefer to be reduced over aluminum, a highly reactive metal. Highly reactive metals want to be oxidized. So, since it's spontaneous, we want our most positive one to be reduced. So we're going to leave that the same. And 2 electrons going to 2I minus. Now this would be a tricky cell to build, and honestly I'm not sure how we would do this, but I'm going to give you the cell notation. 0.53 volts. Now I'm going to reverse the aluminum because it's going to be our oxidation, and I would oxidize aluminum to aluminum ion plus 3 electrons. Therefore I'm going to change the sign, and when we add that up, you get 2.19 volts, which it's positive. Indeed, it is a spontaneous situation. We want to balance this, so we would have to multiply this by 3 and the aluminum by 2. And so our balanced overall reaction would be 3 iodines plus 2 aluminums. The electrons cancel. We set those up to cancel. Will give us 2 aluminum ion plus 6 iodide ions. So we're balancing very simple ones for now. If we did delta G naught is equal to minus N, which is 6, F, Faraday's constant, E naught, which is a plus 2.19. And if I did my algebra right, if I didn't, I know you're going to tell me that. I have here 1270 kilojoules. Wow, it's a big hunk of a change there. Now, let's look at how we would write our notation. We always do the oxidation on the left for cell notation. Cells aren't always drawn that way, but cell notation is always that way. So we have aluminum solid. We're going to have a phase boundary, so I need a line here. Then we are going to have aluminum ion, and either 1 molar or possibly just the word AQ in there. Then we need our salt bridge. 1, 2. Now, what we do with this half reaction, iodine cannot conduct electricity. So we're going to put a comma between those, and my iodine aqueous, assuming we're still standard. And therefore, I would need some sort of inert electrode because iodine, I too cannot conduct, so I'd need platinum or maybe graphite as my inert electrode. So that would be my cell notation. All right, I want to show you at least one non-spontaneous one, so we will do that in the next video. So until then, you got it, kiddos. Signing off. Take care.